All right. 62. And pretty darn close there. We have a node here. Node here, node here. We got an antinode. Doing a fine adjustment here to see if I can. Load it down. Somewhere around there. And 63.2 is what I'm getting. And there's lots of places that could be a little bit off. Also noticing that this is leaning forward, which it wasn't when I did my measurement. So L is a little bit smaller, which would make that a little bit bigger. Okay. What the heck? Let's do the next harmonic. What frequency would get the third harmonic? And again, this is the number here that's going to change. Yeah. What frequency gets me the third harmonic? Let's go ahead and get it to 93.02. 93.02?
Yeah.
All right, so 93.0 says I can only go to a tenth here. Hold on. Third harmonic. What's up? Short circuit something? All right, let me do a quick test to make sure that this is still functioning. Okay, that's still functioning. There we go. Oh, and reset that. 93.0. And do we have a third harmonic here? That's not great. There is a node. It is, I have an antinode here, antinode, antinode.
I don't see anything.
I see some.
Let's see, do the fine tuning.
Oh, I see it. Great job.
Gosh, thanks. And I got 95.1 here, so off by 2 hertz. Hopefully, some evidence that, again, what I'm going over right now is not complete BS. Questions? Because we're about to use, I think I can almost safely say, every physicist's favorite toy. All of you know it. It goes up, downstairs, alone or in pairs, and makes a slinky sound. It's a spring, a sling, a marvelous thing. Question is it still sitting out, or did it actually get, an empty box?
Back to the
All right, why don't we
lab.
take 5 while I hunt down the Slinky? Oh, and there's duct tape here. So Slinky has been sitting in this room for probably
You had
a
it
year.
on Thursday.
Pardon?
You had it on Thursday.
I know. Somebody actually put stuff away out there.
That's perfect.
Take a sec.
Wait, what?
I'll just do my
She was asking like Thursday before midnight.
Yeah.
11:50. Like, can you turn stuff in until that?
Okay. We can.
All right, simple
Yes.
harmonic motion. Simple harmonic motion is ideal, so let's sort of hit what the words mean. Simple, frictionless, in essence, ideal. Simple, the fact that we get rid of a lot of real life. For instance, an ideal spring, this thing would never interfere with itself, but as you all know, it will eventually hit coils, will hit coils, and we don't have that in our nice ideal spring. Harmonic, it's repetitive. Motion, it's moving. I don't think it really counts as simple harmonic motion if it's sitting there in static equilibrium. So I need something that's going to move in repetitive motion, ideally forever. Now, this is going to go for a while, so there's ways of dealing with that, some of which is beyond the scope of this course, some of it is not. In simple harmonic motion, an object will obey Hooke's law. So, an object in simple harmonic motion obeys Hooke's law. Hooke's law says that as the stretch goes, so goes the force. That is the English translation of the Latin anagram that Hooke did in order to claim rights to it. In essence, the force is proportional to how far it's stretched from equilibrium. So the force, this is, put a little S there for spring, it's an elastic force, but F sub E is electric force. The spring force is equal to negative K, it's a lowercase k, delta X.
Can you repeat how you worded that? Force is proportional to how far?
It stretches.
Oh, sorry.
Now, so that's in essence what we have here. This K is a spring constant, known as the spring constant.
This is not a dot product.
It is not. This is, K is a scalar multiplied times a vector.
Is this like the elastic energy formula?
Yes. It's not that, but it's similar to.
Yeah.
This is a conservative force, and so therefore there's a potential energy formula, and that's 1/2 K delta X squared, which you've been introduced to. So K is a spring constant, it's a stiffness constant. The larger the number, the stiffer it is. It would be something like 40 newtons per meter, which means it takes 40 newtons to stretch it 1 meter. It takes 80 newtons to stretch it 2 meters. The minus sign is there to indicate that the force is back towards equilibrium. So if I've got my spring right here, if I pull it down, I've displaced it downwards, but the force that that coil exerted on that bottom coil is upwards. The force is always back towards equilibrium. If I pull up on it, then the force on this, that the spring exerts on this coil right here is down. So the force is opposite the direction of the displacement. Now, if I have a nice ideal spring in my ideal world, and it's oscillating in simple harmonic motion, then that force has to be the total force, the one famed in Newton's second law. So what would that be equal to?
MA.
I think I just heard it.
MA.
Yep. So I have negative k delta x is equal to mass times acceleration. What's the formula / definition of acceleration?
Acceleration due to gravity.
No, acceleration. Chapter 3 definitions,
Oh.
chapter 2.
Changing velocity over changing momentum.
So that would be equal to the mass times the change in velocity over the change in time. What is velocity?
Displacement over time.
Okay. So that's going to be the change over the mass times the change over the change in time of the change in my position over the change in time, which we can shorten the abbreviation. The math is put delta squared x over delta t squared. If you've had some calculus, you'll notice this is somewhat familiar to a second derivative. If you haven't had calculus, when you take it, you'll go, oh, yeah, I've seen something like that before. This is just shorthand notation. I know velocity is the slope of my position graph. I know acceleration is the slope of my velocity graph. So what I'm looking for here is some function so that when I take the slope of my position graph, I get pretty much the same shape. Can anyone think of a function? If I take the slope of that function, I get a shape that's pretty much like I started with.
Sine function.
Let's see if that works. So a sine function looks like this. If I take the slope of that, I know my slope is 0 here and here. I have a positive slope, then a negative slope, then a positive slope, so that's going to look something like that. If I take the slope of this graph, my slope is about 0 there, there, and there. And then I have this big negative slope to 0, positive slope, and so it's going to look something like that. It does look basically like what I started with, except the fact that it's a flip of it, which is okay because I got a minus sign right there. And so if I have something that obeys Hooke's law, it's going to vibrate in simple harmonic motion, and therefore it should be moving like a sine wave or a cosine wave. Cosine also works. So if delta x is equal to some sine wave, we'll just keep it simple for now. So I have this function right here. The question is, I was just looking at the basic rough sketch over there. But how do these affect the slope?
The A increases the at altitude, so like it
Amplitude.
Amplitude, whatever. But it goes up or down depending on what's the sign, and then the W is
All right. So if I have a value of a that's bigger than 1, this would look something like that. What is that going to do to the slopes?
increase it.
Yeah. Matter of fact, if this is twice the amplitude, this will be twice. The slope will be twice as big as it was. What about that omega? That omega right there.
It changes the period. So
How?
well, it's equal to 2 pi. So I don't remember.
So if I have a normal sine curve, just y equals sine of x, or make it sine of t. What is the period?
2 pi.
agree with them?
Yes, it's too high.
Okay. All right, so if I have y is equal to sine of x, sine of t, then that would be 2 pi. That's y t. If I did y is equal to the sine of 2t, what does that do to my graph?
It shortened it to having just a period of pi.
So in essence, if connecting this to something more physical, is that if I have a wheel rotating about its center, I have a peg right here, and I have a light source above, so it's casting a shadow. The shadow is going to be moving back and forth in simple harmonic motion as this wheel rotates around like that. If the wheel is rotating at an angular speed of omega, the shadow is going to move back and forth with an angular frequency of omega. This omega here, and I threw it on the floor. This is the angular frequency. It uses the exact same symbol as angular speed. It has the exact same units as angular speed. It is a philosophical difference. That the wheel rotates with an angular speed, casting a shadow, which has an angular frequency of the exact same value.
Was that a 1 under it, or just the line that you had drawn?
That right there?
Well, before you drew that arrow for angular frequency, there was a little dash under it, was that a 1, or?
Just a little dash under.
He had accidentally touched the screen, pointing to the W, and then
Okay.
yeah, I just drew a line.
So, are the units radians per second?
Yes, they are. So if omega is 2 radians per second, that means that this wheel is spinning twice as fast, which means that the shadow is moving back and forth in half the time. So Robin was correct that what that does, apparently that's not the one I was just working with, is it makes the shadow, it basically oscillates it where that's 2 pi, that's pi. It shrinks it this way. And more specifically, the period is now 2 pi divided by 2, or pi, or in general, the period 2 pi over omega.
Is that supposed to be sine 2t?
Say it again? That's sine of 2t, yes. So if I take my graph and I squish it in like this, what is that going to do to my slope?
Make it steeper, like
Yeah.
increase the slope.
As a matter of fact, what it's going to do is make it steeper by the factor of omega.
So if you did if you multiplied by 0.5, it'd get longer.
If omega were 0.5, yes, it would stretch out. So we are left with, if my position graph is some amplitude sine of omega t, then my velocity graph, which is the slope of that, which goes from sine to cosine, is going to be a omega cosine of omega t, which, and my acceleration is going to be a omega squared negative sine of omega t. Every time you do the slope, you multiply it times another coefficient of the time.
Wait, can you say that again?
When you do this, whenever you take the slope of a sine function or a cosine function, whenever you're multiplying by t, that gets multiplied
Oh, okay.
out. So I got a negative a omega squared sine omega t. This would be this is the amplitude of my acceleration graph.
Is the first one, I have the first one that you wrote up there as delta x equals a sine. Did I write it wrong the first time? Are they the same?
No, I'm using them interchangeably here, I shouldn't. Plus, there we go. All that does is shift the graph up and down, it does nothing to the slope whatsoever.
Okay.
So this is setting it so that I can start anywhere, therefore making a position and not necessarily displacement.
Okay.
If I add a cosine, instead of doing sine, I did cosine. So if x is equal to a cosine of omega t plus d, then my velocity is negative a omega sine omega t, not plus d.
Yeah.
And then acceleration is negative a omega squared cosine of omega t. The order of these trig functions, sine to cosine to negative sine to negative cosine, and then repeats. Questions here? Next. So plugging into, we have negative k delta x is equal to ma. I'm assuming because it's harmonic motion, it can be modeled with a trig function there. So I'm putting delta x here. I'm going to assume it starts at 0, so d is 0. So negative k sine omega t is equal to mass times, there should be a capital A there, capital A omega squared sine omega t. Thank you. Take a moment to convince yourself that there's